I will go through the assignment slowly. I will try to explain everything underway. And let's begin if you don't have any question. Um, you can use Jupyter Notebook or other IDEs, whatever you want. But I personally will use Kaggle.com. There is a possibility to use notebooks freely and without downloading anything. So just I created a new notebook. After creation the notebook, the first thing we have to do is to add data, right? I have not added the data because I want to show you how you can use Kaggle. You can add the data from your computer after clicking Add Data section here. As you can see, you can search by URL, or it will search through the internet, find the solutions, find the data for you, or you can upload from your data set. For example, in this assignment, I will upload from my computer. If you want to, I will show you how to upload from your computer, browse files, and try to find out the location of the data. And my data is inside this data. After you choose the data you want, open it, and give a name for the data set. Let's say this one, assignment 2 data. It's not important, you can give either name. And after that, please click on the create button. As you can see, it's now uploading the data and successfully. After a couple of seconds, on the right side of the Kaggle, you will see your data as you can see here. This is the data. Click on the data set. This is the data I want to use, right? So there is a copy file path section here. Please click on it. Okay. Now we have copied the address location in the Kaggle, and after that, it means that we can use it. But before we use the data set, first of all, we have to import NumPy and Panda. In the Kaggle, it automatically is the first code. So just click Run button. But if you don't have, please import NumPy as MP or import Panda as PD or whatever alias you want to use. And after that, the second step is to create a data frame, right? Because in a machine learning algorithms, we will use Pandas data frame. So we have to create a data frame. So in order to create a data frame, I am using PD. This is the shortcut of the Pandas, okay? PD dot, first of all, we have to read the file, right? In order to read, this is a CSV file, so I will use CSV and open brackets. Inside the brackets, I'm writing quotation marks, and between the quotation mark, I'm just pasting the data file location. Previously, I have copied, right, and paste it here. As you can see, it has copied and pasted the exact location of the CSV file inside the Kaggle. And after that, when you click and run button, yes, as you can see, this is the original data set we have. So this is not enough because I have to assign this one into a variable name because I want to use this one and its methods. But in order to use the methods, in order to work with the data, I have to assign that one into a variable name. I'm just writing data frame df. You can write whatever you like. And now when I write df, as you can see, the data has been imported and assigned into the df variable name. Yes. Let's go through the data. Let's see the columns. df.columns will give us the column names of my data set. As you can see, all of these are columns of my data set. Okay, so the ID column, and there is a column name unnamed, I think, and it is not required to use this one. So after importing the data set, we have to get rid of the unnecessary data, right? So the ID means nothing for the machine learning algorithm. So if you use these different kinds of IDs without dropping them, the algorithm will evaluate this data as an important data, like diagnosis, radius, mean, and the other columns that are important. So this is not important for us, right? So I think it is better if we just drop this one. In order to drop that one, it's very simple. We are writing our variable name, data frame df dot drop method. Okay. Inside this drop method, I will just write the name of the column that I want to drop it. And the second step is write the axis parameter as 1, because I want to drop a column. Okay, if you in pandas, if you want to drop a column, you have to specify the axis as 1, which means column. If you use axis is equal 0, it means rows. So it will not drop if you write here axis is equal 0. So I have to specify as 1 because I want to drop a column name. And thirdly, there is another parameter, in place parameter, right? So I will explain to you. If you use that one, let's use it. As you can see, the ID column previously is the first column name, right? And now after I am using that code, we cannot see the ID. But if let's add another code and let's look at our data frame. As you can see, the ID column still stands here because Pando wants to check you, are you sure or not? In order to get rid of this data, you have to use in place parameter as true. It is by default false, therefore it will not drop from your data. So I have to write this one as true. After doing that, right, let's look at that one. As you can see, we cannot see anymore the ID column, right? Let's look at how many missing data we have in our data frame, right? df.isNull will return to me whether there are missing data or not, but it will return Boolean values. But I have to use sum in order to see how many missing data each columns have. So as you can see, all of the columns, almost all of the columns, except from the unnamed 32, has not any missing value. So which means that I have already the length of the data is already 569 rows, right? Which means that this unnamed 32 column has full of missing data, right? So it means nothing for the algorithm. We have to get rid of this one also. Let's get rid of that one. df.drop, use it, and after that, let's copy the name of it. Okay, so it's a very interesting name, and paste it. And it is a column, so I will specify axis as equal 1. And after that, I want to in place that one forever. So I'm using in place parameter as true, right? Let's run that code and see. see our data frame again. Yes, as you can see, the unnamed column was at the end of the data frame, so we cannot see it because we used in place as equal parameter, and we have get rid of this unnecessary data forever. Okay, now when we run this code again, this one, in order to check again whether is there a missing values or not. This is very important. After the importing the data set, the first step maybe is to find out the missing values, right? So as you can see, there is no any missing values, which means that now I don't need to do any data engineering to fill the missing values, okay? So it is ready for the algorithm. So the next step is, let's find out, yes, the second step is let's explore our data first of all. Okay, what kind of data we have? Let's run our data frame again. Okay, df.info method will return to me information about the columns. Okay, so as you can see here, all of the columns data type, this is data type, are float 64, which means they are numerical data, except from the diagnosis, which is represented by object, which means object represents strings. Okay, let's look at our data frame again. As you can see, diagnosis has been labeled as M or B, which means which represent M represent malignant, B represent benign tumors. Okay, so in the deep learning, we cannot work with the strings. So we have to also transform this data into numerical data, okay? And I will show you how can we do that. But before we go further, let's explore our data a little bit more because it's very important. In order to get some statistical information on our data, we use describe method. Okay, if describe, let's run that code. As you can see, all of the column has been listed here as inside as a table, but we see the count of the elements, which means how many values they have. As you can see, count represent, this is the represent number of rows each column has, which is 569. The mean of the column, for example, the mean of the radius is 14, or approximately. The mean of the texture is 19. So we can analyze the data, what kind of data we have here. We can see by using single code, we can get all of the statistical information of our data set, right? This is the STD, means standard deviation. So for example, standard deviation of the first column, radius mean, is 3,5 approximately. So we can see that if I add this one, the mean standard deviation, which means 17 almost, also, or if I subtract this standard deviation from 14, which means 11, so I can understand that this column, the data of this column is distributed between 11 and 17. Okay, we can apply the same understanding of the other columns. If I add 2 times standard deviation into the mean, or if I subtract 2 times standard deviation from the mean, I can get 96% of the data distribution of this column. So it's very important to understand the data, because if we work in a company, we have to write reports also. So it's very important to understand what kind of data we have, what is the relations. So this is the minimum, mean represent minimum. minimum value. So we can easily see minimum values if each separate columns. We can see uh, um, this is, as I said, this is the standard deviation. This mean minus standard deviation gives this is the lower band of the data, which means 20% of the data is under 11,7 for this data, or 16% is under 20%. 20% of this column has been under 16, okay? Which is, this one is calculated by subtracting standard deviation from the mean. And 50% means 50% of the data is around this value, okay? And this is the upper bound of the standard deviation, which means that after this number, the 20% of the outliers has been distributed after this number, okay? And maximum gives us the maximum value of each column. So as easily we can say that the maximum radius mean is 28 approximately. The maximum value of the texture mean is 39 approximately, and so on. You can see all of them. So this is very important. So we get a good understanding of what kind of data we have. After that, it's also very important to see what is the relationship with this data, okay? So in order to calculate the relationship, we use df that core method. Let's run this one. This will give us the correlation between each single columns. For example, the correlation between radius mean and radius mean is 1. Correlation is distributed between -1 and +1, okay? And each values has been distributed between -1 and +1. So if it is close to 1, which means perfect correlation, perfect positive correlation between the values. Of course, the radius mean itself is a perfect correlation, which means 1. But when it comes to correlation between radius mean and texture mean, as you can see, 0,32 approximately, okay? For example, you can easily see that the correlation between perimeter mean and radius mean is almost close to the 1, right? 0,99 approximately, which means that there's a perfect correlation between these two variables. If this one increase, this perimeter mean also will increase. If radius mean decrease, perimeter mean will also decrease relatively, and vice versa. And if it is close to -1, I try to find an example, which means there's a negative correlation. I couldn't find, but there are some, yes, for example, this is a little bit good, which means that if someone is increased, the other one will decrease, or if someone will decrease, the other one will increase. There is a negative correlation, okay? For example, fractal dimension mean and radius mean, there is a negative correlation, which means that if we increase, if the fractal mean, the dimension mean increasing, the radius mean will decrease, okay? They affect with each other negatively. But if the correlation is close to 0, which means there is no correlation, it means that these variables, these columns will not affect each other. Let's find it an example very close to 0. For example, that one, okay, that one is very close to 0, right? Or that one. Which means that fractal dimension, and let's go up, area mean will not affect each other, okay? So this is very important. We get a very good understanding of data, but the most important thing I want to find out the correlation between my target column. My target column is diagnosis, right? In the DF correlation function, we cannot see this my target column, diagnosis column, because it includes strings. It does not include numerical values. The correlation method will return us the correlation between the numerical data. So if I want to find out the relationship between diagnosis and the other features, I have to transform. Also, in order to apply machine learning algorithm, I have to also transform this target column, which includes strings as malignant or benign, into numbers, right? So let's do that. Let's transform our strings, our target column, into numerical values. We have did this one before. Let's from scikit-learn that preprocessing, from preprocessing, yes, it comes when if we click on the tab button, it comes. Let's import label encoder, label encoder, label encoder. Yes, that one will return will return labels into the numbers. Let's run that code. If you remember previously, after importing this one, we have to create an object of it. Okay, let's write a shortcoming of it, an alias le, which represents label encoder, is equal. I'm just creating an instance of it or an object of this function. Okay, encoder. That's good. Now, which means that after running this code, I can use this label encoder by using this object, okay? Any function, any method with this one have. And the column I want to transform is this, my target column, right? Let's use it. LA dot fit transform. First, this method will first of all fit the data and transform this data. Fit means which will explore the data beforehand, what kind of data this one has, and after that it will label zeros, ones, or twos according to the what kind of category this column has. Okay, so fit transform. Let's do it. Transform. My column name is df.diagnosis, right? If I, yeah, not to upper cases, but lower cases, diagnosis. Okay. I think that one, yes. Let's run that code. Yes, as you can see, it has fit and transformed the data into numbers, right? But this is not really, because I have to assign the result into the variable name. The variable I want to change is df diagnosis, right? So let's apply this function and assign the result into table again. Let's copy that function again, and now the result, which is an array, will be assigned this df diagnosis column. So I will change forever the diagnosis column from M or B, which represent malignant and benign, into the numbers ones or zeros. Okay, let's look at our df again after transformation. As you can see, diagnosis has been changed into ones and zeros. If it is 1, which means malignant, and if it is 0, which means benign tumor. Okay, so I am almost ready. All of the columns are numerical. So let's look at correlation again. We have correlation, and because I want to see which of these features affect the cancer tumor. Okay, it was very important. If we work, the doctors will try to understand what kind of features affect the cancer tumor most. I can find out this one by using this function, because the correlation, I have to find out the correlation. As you can see, diagnosis has been written here, and of course it had itself 100 perfect correlation, but when I come to this area, I can see every single correlation of each columns with diagnosis with my target column. Let's see that. I can easily see that, for example, concave points mean is a good correlation, right? Very high positive correlation with the cancer tumor. And let's go a little bit right. I try to find out more higher values. Okay, let's use that one. I'm not sure it will work. No. Yes, of course, it turns maximum values with itself. So the maximum correlation is 1 with itself. Yes, this is a good one. Maybe this numerical value can be a little bit complicated, okay? So we can visualize this one and easily understand this correlation. Instead of going through each column, we can easily visualize this result. How can we do that? Let's, of course, we have to use visualization libraries. Let's import matplotlib. This is the most common used library in machine learning. .pyplot, okay, splt, and let's import Seaborn. Seaborn a little bit enlarged or a powered version of matplotlib, but Seaborn has picked up matplotlib, so it has better features when we compare to matplotlib. Let's import Seaborn as SNS. This is the common alias that developer use. I think Seaborn, import Seaborn as SNS. Yes, matplotlib, there is a yes, pilot, not pilot, pyplot. So let's run that code again. Yes, let's use a big figure size, okay? plt.figure. Now I'm using matplotlib, okay? I'm creating a big figure size because I want to see that one in a big figure. Let's assign these values in order to get bigger figures, okay? So after that, I will use a Seaborn's heat map. Heat map. Inside this heat map, I will assign df.correlation because I want to see correlation inside this heat map, okay? Also, we can change default CMAP. CMAP is a parameter which assigns the colors of this heat map. Let's use, for example, first of all, not use any CMAP. So let's use that just by default in order to explain you the difference. Let's run that code. As you can see, now we can see the correlation between each single values features with the diagnosis in a map. As you can see, there is a legend here which represent positive, which if the colors comes to this color, right, which means positive 1 perfect correlation. If it comes to this area, it will represent negative correlation, okay? So as you can see, diagnosis, for example, this one almost 0.8, right? The color is very close to the 0.8, which means 80%, 80% correlation, as you can see, that one. Let's look at which this value is. For example, radius mean is very highly correlated with the diagnosis. So you can easily see that, okay, if someone else's radius mean, according to the doctor appointment is very high, or Röntgen is very high, which means that is a risk of highly diagnosed as cancer, okay? So for example, for this one is very close to 0, right? So we can easily see that there is no correlation between diagnosis of cancer with this one. Let's go down. Fractal dimension mean is not correlated because it is very close to 0. And if it close to this color, a little bit dark color, which means that there is negative correlation. Okay. For example, very dark, the radius mean here, as you can see, very dark, is very negatively correlated with fractal dimension mean. So it's a good analyzing. Okay, let's write CMap. We can change the color of this heat map by using CMap. Inside quotation marks, you can go from the internet and Inferno, for example. I will use Inferno. I like it. There are a lot of different kinds of CMap which will change the color line. Okay, but for example, that one seems like this one. We can use Magma, for example, another CMap. There are a lot of options you can try. Let's go down. So we can easily analyze for our reportings. Is very important to understand the data. Okay, it's not, our job is not simply implementing the machine learning algorithm. Also understand the data, because we will give a report about the results of these operations, right? Yes. So there is no, we have dropped the unnecessary columns, we have analyzed the data set, and there is no missing values, which means that now we can separate our data as features and target. Okay, I generally use X. It is very common case among the developers for the features, and Y for the target column. Okay, you can write here target, it's not important, but I simply use this one. Okay, if I drop the target column, which means diagnosis, the rest of the, let's delete this one. I will show the results. Diagnosis on axis equals 1. Let's see the results. Okay, as you can see, it has dropped the diagnosis and listed the rest of the columns, which means that if I assign this result into X, I get the features of the data set. Okay, so it's a good way. Let's try to write the X and run that code again. Now I have assigned all of the feature except from the diagnosis into the X variable. Okay, and after that I need also my target. Okay, I will assign the result to the target. df.diagnosis is my target. Okay, diagnosis, this one, as you can see, and I will simply assign the result into my Y variable. Okay, let's see the Y. Because for the assignment, also for the training of the machine learning algorithm, I need to separate my values into feature and target, because I will split these results into training and test sets. Okay, so this is a necessary step we have to deal with. Yes, now my data has been separated as features and target. Okay. But there is another important thing we have to deal with. As you can see, X is, when I write here X, this is a pandas data frame, right? But in order to deal with the machine learning, deep learning algorithm, we have to transform this data frame, which is a tabular format of data, into NumPy arrays, because the deep learning algorithm only understands NumPy arrays. How can I do that? It's very simple. Just if I write here x.values, will transform all of the values, this data frame, into pandas NumPy's arrays. Okay, as you can see, this is the result. So I will assign the results again into X, which means I will change X because I don't need X as a data frame. I need X as a pandas NumPy arrays. So I'm assigning X dot values, this pandas format, into NumPy arrays and reassigning X again. And this is my X. Now I have changed the X. It's not anymore a pandas data frame, and it's not a tabular format of data. It is just arrays, NumPy arrays, okay? Which means matrices we have learned in this year's semester mathematics. Yes, let's do the same thing for also our target column. Okay, this is the result. Let's reassign the result into Y and see the result again. Okay, now it is also a pandas from pandas data frame into NumPy arrays. This is a necessary step for deep learning. For normal machine learning algorithms, we don't need to transform that one, but deep learning, we need it. Okay, now it is my data is ready. I have separated as features and my target. I have transformed my features and my target data into NumPy arrays. So before I implement the machine learning algorithm, it is ready, but I have to split this data into training and data set and test data set, because I will not use all of the data for training the algorithm, right? So because I will use some of them for training purposes, some of them for testing purposes in order to understand how the algorithm performs. This is a necessary step. So the size of the testing, simply I will import from scikit-learn model selection. From this library, sub-library, I will import train test split function, okay? Train test split. Let's run that code. Let's print. Let's use help function, okay? Normal pandas Python function. Let's assign this one and see the features, how we can use that function, okay? We have used that one before. Yes, as you can see, split arrays or matrices into random train and test subset. I mean, basically, after using help function of Python, we can see an example of this usage, okay? Let's go down. Yes, this is an example of it. Let's copy this example. Instead of writing from I can write it, but it's important to be practical. Let's copy that one. I don't need this. Okay. Yes, I have already assigned this X represent features. I have already assigned my features into X, so I don't need to change that one. If you assign different names for your features, for example, you can assign features as features, you have to write here features, whatever variable name you have used. So I have also used, this represent my target. I have used Y also to represent the target. Test size is 33%, but for the assignment, let's open the assignment. I remember we have to use this percent, 20% for test set and 80% for the training data set, right? This random state, we don't need it. Yes, what this function does, train test split, as its name suggests, splits this X features into X training set and X test set. Do the same thing for the target one and split that one into Y train and Y test. How can I do that? I assign a parameter name, test size is equal 0,2, which means 20%, which means that this function will use 20% of the data into test data set, and 80% automatically will use for the training set. Okay, and let's run this code. Okay, for example, we can easily see the results. Let's see the size of this code, these results. Okay, or shape. I'm sorry. And as you can see, this X train includes, these are the features, column names, columns, 30 columns, and these are the number of rows. Okay. And let's look at the Y train in order to see that it match up, because it has to match up, and see the shape parameter. And let's look at it. As you can see, the number of the rows is similar, but the number of the columns is not similar, because this is the target, which includes only one single column, and we cannot see one here because NumPy will not assign one, and we understand automatically after that comma is stands 1. Okay, so this is the number of features and the number of rows. It matches up, no problem. And let's look at the results of the my X test and shape. Yes, let's look at the Y test dot shape. Yes, it matches up. Let's sum these results. If we sum these results, we get normal. Let's extract shape before splitting. Yeah, this is the original X. As you can see, it includes 569. Okay, let's look at X test size, 114. X training site, 455, right? When we sum these two values, we get my X. So if you get the 20% of this data, we will get this number. So we understand that everything matches up perfectly, so no problem. So my data has been split into training and test data sets, both in features and also my target. Okay, so after this step, I am almost ready. If we use normal machine learning algorithm, we simply use these results and simply apply to the machine learning algorithm. Okay, let's do that, because in the assignment, the professor wants us to use the decision tree algorithm. Okay, for example, you can simply use decision tree algorithm here. Let's import that one from scikit-learn.tree. Import decision tree classifier. We have to use classifier algorithm because it's a classification problem. We have to predict whether a tumor is benign or it is malignant. Okay. After importing that one, let's use we have to use, it's very simple, we have to create an object of it, or an instance of it. Let's use, in order to use the function of the algorithm. Okay, yes. After that step, after importing and creating my object, the step is very simple. Decision tree that fit. We make the algorithm fit my data. Okay, first of all, I have to I'm using this fit function for my training data set, because first of all, I have to fit, which means I have to train my data. In order to train my data, I will use my training data set. Okay, first of all, I will write my features. my features of the training set has been, I have assigned this X train. As you can remember here, I separated and assigned features, training and test data set. X train represent the features in training data set, okay? And also I will use, this will fit. How can it fit? It has to know the why. It has to know the algorithm should know the results, okay? Which means on my target. The result is my training. I have to use my training Y set, okay? Because it has to match up. If you use, we have to use, in order to train our algorithm, fit method, and also we have to use our training data set. Our training data set is being represented as X train and Y train. First, I will use these X train features, and after that, it will predict this Y train and create an algorithm, create a function to predict best Y my target data. Okay, let's do that. As you can see, the algorithm works. After the next step is decision tree. Decision tree that predict. Now it's very simple. We will just predict. What will we predict? We will predict the test data. Okay. I will write here the features of test data, and this function automatically will try to test Y test. Okay. So we will not write here Y test, because the aim of this predict function is to predict the prediction, to test the prediction of the algorithm, whether it is close to my Y test or not. So I'm just writing here X test. For example, these are the results. Okay, let's look at the original data. Y test. Yes, as you can see, a lot of them match up. Okay. Yes. So it's very simple. We can simply, after this, if we use normal machine learning algorithm, without any standardization, without any normalization, we can simply use the data. Okay. But when it comes to deep learning, we have to make the data normalization. It's very simple. We know how we can standardize our data, which means I have talked about how we can standardize normalize data, which means that some of the features may be very close to 0 or minus 100. Some of the data is between 1,000 or 1 million. So there is a huge gap between the features. Okay, so this standard scaler, we will use standard scaler, will standardize this data. So it will, there is a couple of function of it. It will, for example, find out the mean of the data, and it will divide each value inside each single column into this mean. So it will get a standard very close to 0, or it find values very close to 0. So at this, by using this method, because the data for each features will be represented between -1 and +1, so there will be no huge gap between separate columns. So the performance of the deep learning algorithm will very increase. So this is a necessity in order to get a good prediction when we use deep learning. It's very simple. There is no need to be afraid of it. Just we will import cyclone dot preprocessing library, which means if you want to make some preprocessing about your data, we can import any function from this cyclone preprocessing sublibrary. And this time I will use standard scaler. Okay, standard. It comes automatically if you click on the tab button. And the second step is just create an object of it, or an instance of it, and shortly name this one SG, and is equal in creating an object of it, standard scaler. Okay. So after running that code, by using this SG alias, I can use any method of this function, okay? Of this class. You can also name that one as a class. It's not so important. This is very important. I will standardize only my features, not my target column, okay? The first step is just the same function, fit transform. Sg.fit transform, let's have it, okay? My X train. It will fit and transform this. It will first of all fit the X train dataset and transform this dataset according to its inside algorithms into numbers between -1 or +1. Okay. So the results I want to change the results X train. I will assign the results into X train again because I want to change X train. Okay. For example, if let's look at previously X train before applying the function. X train looks like this, Let's run that code. Okay. Looks like this one. There are different gaps. Some of the numbers is very huge. Some of the numbers is very small. But after applying this standard scalar, let's look at X again, X train again. Okay. As you can see, for example, let's look at the first one, which means 1,4 times 10. Okay, this one 10. For example, this one minus 10. When we compare that one, as you can see, all of the results is very close each other. There is no huge gap. But when we look at the previous one, some of the numbers is very high and very big, and some of them is very small. So this is not good for our algorithm. We have seen the results, this normalization result in also Veka. We will see this result also here. Now I have transformed my X train data set, and I have to do also, if I normalize the data in my training set, I have to do the same process for my testing data set in order to get the effects. If you don't use this normalization, if only apply for the training data set, you will not get a good results. So I will apply this normalization only my training data set, but it should be both for training or also test data set. Okay, so let's use the same standard scalar for because it has already fitted, it has created its function according to this data set. So I don't need fit transform method again. I'm just using that fit sg.transform my X test. And please assign the results. I want to change my X test according to this new result. Okay, let's look at X test again. Before applying the code, let's look at previously X test. This is the previously X test. This is the result after applying X test. Okay, so as you can see, the numbers has been changed in a very standardized normalization. So which means that my data is ready for applying deep learning now. I can use any deep learning algorithm for this purpose. Let's get 2 minutes break, okay, if it is suitable. I will get a couple of water, and after that we will just build up our artificial neural network and see the results and compare with the decision tree. Okay, just 2 minutes. Yes. Okay. Let's continue. Now our data is ready for building up our neural network. Okay. First of all, we have to create a sequential line because neural network, as you remember, has been built up a sequential line of hidden layers. Okay. So we will import sequential class from TensorFlow. Let's import that one, TensorFlow .keras .models. This is the type of model. If we use artificial neural network, we have to use sequential. Sequential. Okay. Let's run that code. And let's also import from TensorFlow TensorFlow.keras layers. Now I am importing a class that enables me to create layers. Okay. This is models. This is model type, a sequential model type. This give me the important function to build up my layers. Okay, hidden layers, input layers, and output layer. Import dense layer. I think at tensor, yes, there is a yes. Actually, this dense layer is commonly used because it creates regularly connected neurons with each other, right? Also, it creates layers, but inside layers, each layer is connected regularly, which means every feature has been connected to every single neuron and regularly. So dense is very used for artificial neural networks. And after that, let's create an object of my sequential model. Okay. I will name that model as artificial neural network NNN. You can use whatever you like. Sequential model, right? Now when I run that code, I have a model, and which is represented by alias NNN. It's a sequential model. Now after that, after deciding what kinds of model I have, it's a sequential model. For these kinds of problems, we use sequential model. And after that, I will build up my hidden layers and my neurons, okay? So just I will use add NNN. This is my object. Just add. I'm just adding now. I'm just building up, okay? I'm adding a dense layer. A dense layer. Inside this layer, I can use units parameter, which enables me how many neurons I want to have. Okay. So I personally use, if you remember, our features has 30 features. Okay. So in order to create first hidden layer, okay, first hidden layer, I namely use the same number of the size of the features. Because I have 6 features, I create I'm sorry, 30 features. I will create 30 neurons for the first hidden layer. Okay. So and after that, now we are creating our forward propagation. Okay. So we are creating, first of all, the first hidden layer, and after that, number of neurons, and after that, forward propagation. Forward propagation, I need an activation function, okay? So activation as a parameter has been inside this dance function, okay? I will use relu activation function, but actually there are a couple of activation functions. For example, hyperbolic tangent function, logistic function, softmax function, rectify. This is a short version of the rectified linear unit function. It's very good for classification problems, so I will use that one. And after that, we can run that code. There should be an activation relu. Yes, maybe. Yes. I'm sorry. I said this is a part of dance function. So, but I write this one. I have to write this one inside this dance function. Okay. Let's run that one. Yes, it has been added because it's a parameter part of this dance layer. Okay. Now I have created my first layer, which includes 30 neurons, and I will use activation function, relu function, rectified unit function. Okay. So the next step is I can add another layer, another hidden layer. I will use the same thing again, nnn dot add, for example. I have this nnn add will add another hidden layer. This dance inside the dance will I'm sorry that I changed it. Will make number of neurons. How many neurons I want to add this hidden layer? Okay. So I'm using dance again. I will simply use the same things, but I will change number of neurons here. So instead of writing again, I'm just copy and paste it. For this kind, I personally prefer to divide the number of first hidden layer into 2, and which means I will get 15 number of neurons for this hidden layer. But you can play with these numbers. Okay, it's not problem. In order to you can find out the best number of neurons for each hidden layer. But for my first trying, I will use that one. Situation, yes, it should have a quotation mark here. Yes. Now I have added that one also. Now I will add let's copy that one, my output layer. Okay. Now I am building up. This is my first layer, first hidden layer, my second hidden layer, and I will now create my output layer. My output, as you remember, is should be either 0 and 1, because I will predict the diagnosis as malignant or benign, right? So number of units should be just 1. We will get just one output. Okay. Yes, activation function. As you can remember, sigmoid function will return me results from between 0 and 1. So it is very suitable for me. Let's look at how it looks. Sigmoid function. Maybe when you see that, you will understand better. Let's look at it. As you can see, a sigmoid function This is not a sigmoid function. Yes, let's look at that one. As you can see, sigmoid function assigns whatever input it has, it will assign, it will create, it will output values between 0, okay? Let's look at the y, between 0, starting from here, and increasing up to the 1, okay? So because my output should be either 0 and 1, malignant, if it is malignant, which means 1, if it is benign, which means 0, okay? So for this purpose, sigmoid functions performs suits best for this data set. So I will assign the final output one single output. So either 0 and 1 or values between 0 and 1. But it should be just single one. Okay. Now I have created all the units, all the layers, number of neurons, and what kind of forward propagation I will do. The next step is how to import what kind of function I will use. How can I adjust the weights and biases? What kind of function I have to use? This NNN object has compile function, which enables us to create the functions for backpropagation. Okay, for backpropagation, what kinds of backpropagation or what kind of gradient descent we will use? We use optimizer parameter inside this compile function, and there are different kinds of gradient descent: normal gradient descent, stochastic gradient descent, mini-batch gradient descent, and basically Adam gradient descent outperforms the other. So I will use optimizer as Adam, and after that, now in this compile function, I am creating how I will create my backpropagation. Okay, for gradient descent, I am using Adam gradient descent, but I have also need my loss function. What kind of loss function I will use? Because I will adjust the weights and biases according to this loss function. Okay, but the type of the loss function is determined by this loss parameter. Inside quotation mark, I will write what kinds of loss function I will use, but it depends on what kinds of data you have. Because our data set, our target value is 0 and 1, right? Benign or malignant. So for this is a categorization problem. So for this kind of problem, we will use binary. So because the output will be binary cross entropy function. Entropy, right? I think if I didn't write correctly, and I will, in order to see the performance, I will use matrix parameters, and inside that one, because I want to see the results as a matrix will show the performance of the algorithm. So I will use accuracy. Okay, percentage of the number of correct predictions, accuracy. Yes, let's run that one. Okay, now I have created almost my neural network. First of all, I created an object of this sequential model, and after that, by using dance function, I'm creating my forward propagation. What kinds of forward propagation I will do? How many neurals I will have for each single hidden layer. This is my first hidden layer. I will use 30 neurons for this by using UNIS parameter, and I'm using activation function as ReLU. And this is my second hidden layer. And you can add a lot of hidden layers. It is up to you. But because I know from the Veka, if we increase the number of hidden layers, we don't need it because our data set is very short, it's very small. So I think 2 hidden layers is enough to get a good prediction for this data set. Okay, so and after that, this is very important. I'm now creating my output layer. My output is just only one neuron, should be only one neuron. So I am assigning one for the units. And as activation function, I will change from relu to sigmoid. Let's look at relu. Why I change it, I will show you. Relu function. Yes, this one is relu function. As you can see, relu function starts from 0 and up to forever. So this does not suit for my purposes, because I will predict 0 or 1. A tumor is benign or malignant. So I need just a function that gives the results between 0 and 1. The segment function provides the best answer. So as I showed the figure, why I choose the activation function for my output as segment function. And after that, I am using NNN. This is the objects of my sequential model, deep learning model. And I'm using compile function. Inside compile function, I am assigning by using optimizer parameter what kind of gradient descent I will use. Adam gradient descent I assign here. There are a couple of optimizers. You can search from the internet and just change this value inside the quotation mark. And after that, I have to use my loss function, okay? Because I will adjust my weight and bias according to the loss function. The type of the loss function is also very important, because it depends on what kinds of problem you have. It's a categorization problem or regression problem. Mine is a categorization problem, but it is also a binary categorization problem, because I will just predict 0 and 1. So there is only two options for me. I'm also assigning matrix accuracy here, which provides for every single layer what is the accuracy of my deep learning algorithm. Okay. The next step is similar for almost normal machine learning algorithm. After that, I will fit. I will use fit function. Okay. As you remember, I also used fit function for decision tree algorithm previously, and I will assign X train here, because I will fit first of all the X training data set. By fitting this X training, I will try to predict my Y train. Okay, and after that, there are a couple of difference between normal machine algorithm. I will also need I have to specify number of epochs on other parameter I have to use inside this one. Batch size is important for me, because batch size enables me, maybe you can remember previous week, when I talk about artificial neural networks, batch size, I assign here for calculating gradient descent. Do you want to use calculate gradient descent for after every single row, or a couple of rows, or at the end of all of these rows? Okay, so I'm assigning here, for example, number of 32, which means that it will calculate gradient descent and this loss function after every 32 rows. Okay, so it is better compared to the other ones. So I have to charge my computer. Sorry. Do you have any question to this point? Yes. So almost ready. That's good. I think, yes. Now I have to specify number of epochs. Epochs parameter gives that result to me. Epochs. I will specify that 100 is enough. I think it's because it's a small data set. I will also use validation data set, which enables me, if I apply this algorithm into the XStat, what it will also result with the testing data set without using the information from the testing data set. Okay, so validation data is a good parameter for me to see, to compare the results when I apply this deep learning into my testing data set. What should the result be? It will give me this information. Inside the validation data, I will use X test, also Y test. So this one, without using the data inside X test and Y test, it just compares the results. Okay, the result, the performance of the algorithm. So it's very important. Instead of using at the prediction at the end of the training the algorithm, I can see instantly results of the performance of the algorithm by using validation data. Right? So it's very important, I think. I think it's ready. Let's train our model. Yes, do you see number of epochs, the loss, accuracy, and validation accuracy? Yes, after the second epoch, do you see the result? Accuracy for the first epoch is 62%, but when it comes to it adjusts itself very good. After the second epoch, the accuracy has been increased to 91%. Okay, and also my validation accuracy, which means that if I apply this machine learning algorithm into the testing data set, it should be 96%, 96% approximately. Okay, this is the results of the losses of the weights and biases. Let's go down. Do you see that accuracy is increasing 99%, and also validation accuracy increasing at 98% after the epoch 2024, right? Yes. I'm going down. It has already, oh my God, after epoch 96, accuracy of the training data set 100%, and validation accuracy 98%. Okay, so the performance of the deep learning is very high. Do you see the result? And when we compare to the decision tree, this is also part of the assignment too, because the professor wants to compare the results. Let's look at the performance of the decision tree. Yes. We can compare that one. Here we have to import from scikit-learn.metrics, if I remember correctly, import, yes, classification report. Now I will see the results of the decision tree. Let's print the results, print classification report. Now I will just using that one for did I assign the results into a prediction variable? Yes, I assigned, I remember. Prediction, the predictions, this is the predictions of the decision tree, if I remember correctly, and Y test. Let's look at the results. No, I have not assigned that one. Let's come to the decision tree algorithm. Decision tree, yes, we have predicted, but we have not assigned. Let's assign the prediction into prediction variable, because I want to compare the predictions with the predictions of the, but maybe it will not match because the testing and training data set does not match it. Yes. Okay, let's run that one. Do you see that? Yes, this is the results of the decision tree algorithm. This is the prediction. This is the Y test. As you can see, the performance of the when it comes to predicting zeros, benign cancer tumors, decision tree performance not good. And I'm sorry, 100% good. But when it comes to predicting malignant, which means ones, the predictions is 0%. So approximately we get a 65% accuracy when it comes to decision tree. But look at the results of the deep learning, 100% for the training data and 98% for the testing data, right? This is the power of deep learning. We instantly see the result and compare it. This is also part of the your assignment in assignment 2. Yes, let's look at the result. ANN.history will give me the history of the training of the deep learning algorithm. Let's look at that one. Yes, we can get the results, the loss functions, but this is not a good solution for me. I will create a data frame, PDF data frame. I'm creating a data frame by using that ANN.history. Okay, this is better, right? I use the same results. Let's look at ANN.history. We'll give entire history of the training process. Okay, but it is not a good one to use because it is a little bit complicated. But when I create a data frame, pandas data frame, by assigning this ANN.history function, I get a very good results and good visualization. Okay, so I now see this is the loss of my training data set. This is the accuracy of my training data set. Okay, this is the number of epochs. If we start with 73% and we are going up, increasing 100% for when it comes to training data set. When it comes to testing data set, validation accuracy, which represent my testing, this is the validation loss, test loss function, and this is the accuracy in test data, and it is 98%. I'm just creating a plot, good visualization. I'm just copied the same function and paste it here. I will just apply plot. This is a good visualization library inside pandas. Do you see the results? Let's get a bigger version of it. plt.figure. Let's say size is equal 19 and 10. It's better, I think. All right. Do you see the results? This blue line represents losses of my my test training data set. This green line, validation losses, and the upper bound represent my accuracy. Okay, the orange one, accuracy of the training set. This red one is accuracy of the test set. Okay, you see that they are very close to each other. But after this point, I think there is no big difference. If I train and more, I will not get a better results, which will cause overfitting of the data, which means that my performance of the training set will increase maybe 100%, but the performance of the testing data will not increase. This is outfitting, and I will explain if we have time to how can we deal with this problem. Okay, for example, as you can see here, maybe from this point, epoch maybe 10, we don't need to train our data. Maybe you can remember, this is also a part of the assignment. You can use wait decades or early stopping in order to stop if there happens a gap between my validation and my training performance. It will just stop number of training to data and give my results. Yes, easily we can get the best results by using evaluate function. Okay, evaluate function. Yes. Let's use extrain. Let's first of all see the performance in training data set. Yes, it will give you the best results. 100% accuracy in epoch 15. You see that? Epoch 15. This is the correct loss function, the result of the correct loss function, and this is the accuracy. Okay, let's use the same function, but inside this function, I will this time write testing data set, X test and Y test. Yes, it will return the best results of the accuracy of the testing data set. As you can see, this is the best result. 98% too, and so on. And this is the correct losses of the best losses of the algorithm. Okay. Yes. For example, if you want to see the results singularly, let's look at my test data set. Okay, the first test data set, yes, I'm choosing now the first testing data set. This is my first testing data set, testing features. Okay, and let's predict the result. I can also predict singularly, just single features. For example, if someone has these features, okay, let's assign that one, the first testing data, and assign here. Let's copy and paste here. Yes, if someone has the feature of this first person, these features, the result will be malignant. Okay, let's look at the original data. Y test, the first element. Y test, the first one. Yes, our algorithm predict correctly. Okay, let's look at the original. Yes, if someone has these features, but please, you should be careful. These are the normalized version of the X test. Okay, so we have changed the data. In order to see the exact results, you may assign. We can assign instead of by using every time X test, we can use before applying normalization. We can separate. We can use different variable names, so we can compare the result. If someone has, for example, this feature, these features in normal version of the data, what will the result? So we can compare the results with the patient's actual results and get the good predictions of it. Yes, also we can make all of the predictions. That's predictions too, because we assign predictions for this prediction of the decision tree. And let's use that one, and then that predict. It is the same for the normal machine learning algorithm. Just instead of using one single feature, we will use entire X test data set. And this will return out the predictions. Okay. I'm sorry, prediction 2. Yes, this is the predictions of my algorithm for entire data set. Let's compare the results with the actual data. Okay. My actual data is Y test. Okay. So what we can do is we can simply create a data frame which only includes the predictions of the algorithm and also X test, so we can compare them better. Yes, let's create a data frame, pd.dataframe, and inside here I will predictions 2. I'm creating now a data frame instead of these arrays. So it is in by using pandas we can transform a data frame into NumPy arrays and vice versa. We can also transform a NumPy array into a pandas data frame, because for better visualization, in order to understand better, NumPy arrays matrices maybe can be complicated. So we can easily transform by using PD data frame function this is a NumPy array into our matrices. We can easily transform that one into tabular form, pandas data frame. Let's name a column name for this one. Columns. Yes, column parameter. Yes, inside that one, predictions. Let's name this one, predictions of deep learning. Okay, and let's assign that one my predictions to again, because I want to change predictions 2 into that one. And now let's write predictions 2 again. Let's run this code. Yes, data frame, of course, it should be uppercase, not lowercase. Yes, as you can see, it's a very better version of my predictions. And now I can transform also the same thing, my y-test. Okay, this is also a NumPy array, right? I will use the same pd.dataframe. I will transform that one into a pandas data frame in order to understand, in order to get a tabular form the results. Okay, instead of using NumPy arrays, let's give this one a column given this now a name. Let's name this original data, original results, or you can give whatever you like. Let's run that code. And these are the results. Let's compare the results. Let's concatenate these one into a single data frame. We can use that one PD data frame. PD dot not data frame that concat function will concatenate these two separate data frame into one single data frame. Okay, I'm just writing here predictions 2, right, and my y-test. There should be a wrong something. Yes, I have specified how I can concatenate these ones in the columns, because not in the rows. Predictions 2. Yes, as you can see, we can easily compare the results of the predictions of the deep learning and the original result. This column represent, on the right side, represent the original data we don't know beforehand, and this is the result of the machine learning algorithm. Okay, so for example, in this, if someone has, for example, in the row 112, if someone has these features, the algorithm will predict 0, because it's a segment function. Segment function will results in values between 0 and 1s. So it will give very close to 1. Okay, so this which means it's 1. I can easily say that it is very close. For example, the last one very close to 0, and we can easily say that our algorithm predict that one as 0, which means benign. If someone has these features, if you come to the at our testing dataset features and then row 113, and if someone has these features, it will have a benign tumor, which means. Yes, do you have any questions to this point? Okay. Let's look at the, yes, we have still time. I will talk to you about, let's create another model, because in the assignment, the professor wants us to use separate experiment. This is just results of our first experiment, okay? Let's create a little bit not abnormal artificial neural network. Instead of going, not that one, we can easily, let's copy that one. Let's copy all of them. I don't need to write every single step. I'm just copying here, but I have to change this one, ANN2, because if I don't change, it will delete the first result and will assign ANN as to ANN for this sequential. So I'm creating another one in order to separate my first artificial neural network. Let's run this code. Go up. For this time, I will just, instead of writing every single step, where is it? Yes, here. Let's use this one. Now I'm adding, it is similar steps, but this time I will use some absurd numbers, okay? For example, number of neurons for the first hidden layer, I will assign 100. Let's create another hidden layer. For example, number of units, let's assign that one. For example, 200. Okay, and 2. Let's add another hidden layer and assign that one 300. Let's run this code. Let's assign another one, and number of units 200 again. Yes, for this time we are creating a very absurd artificial neural network. This is a different experiment for us. Now I'm increasing just only the number of the neurons, number of the layers. For this artificial neural network, I'm creating now 4 hidden layers with very high number of neurons, okay? The first hidden layer, 100 neurons, the second 200, the third 300, and the fourth 300. Now let's create our output. Let's copy from the original one. We don't need to write every time again and again. Let's copy this one. This will be my output layer, and right here I have to name this one ANN2 because yes, after this step we have built it up my first forward propagation. Now I need to create my backward propagation. I'm using add compile ANN compile function for this purpose. Instead of ANN, I will write ANN2. I will not change anything, okay? Because I just want to see the results. Let's train our model. In order to train, we have to use fit the data. Let's take the same information here. Instead of writing from the beginning, I will not change anything. I'm just changing number of neurons and number of hidden layers and see the results in order to compare. Okay. Now ANN2 we should write here. I'm changing nothing. Okay, everything is, yes. We will compare the results. Let's use ANN2 evaluate function in order to see the better results. X-train. Okay. ANN2. Yes, because I changed my X-train here. Let's copy from the previous one. This is, yes, and evaluate X train, Y train. The next step, Y tests. Yes, this is the accuracy of this my absurd hidden layer. Let's see the result for the testing data set. Yes, the accuracy almost similar, even though I have used very absurd number of neurons and hidden layers. The results is very almost similar. Not that, because we get 100% accuracy with very medium size of neurons and hidden layers, which means that this is not an absurd for the deep learning. Maybe we should add much more hidden layers here, but we don't have enough time for that purpose. Let's see the history of this data. Yes, let's see the history. Think we can simply assign here history. We can use the same thing, training our data again and again. Let's see ann2.history.history. This is the results of our second training. Let's assign the result for the data frame. Yes, this is the result. Let's make a plot. Fixed size, assign fixed size as same. Yes, it is a little bit absurd. Do you see that? Which means that there happens nothing. There is a little bit overfitting for this data. After the number of epochs, this is validation loss, right? It's a very similar line, but they begin to diverge from each other after the maybe fifth epoch. But it's not a stored divergence. But when we come to the 100 epochs, the divergence has been increased when it comes to validation loss, and the accuracy is almost similar because the divergence of the loss function is not so huge, so it will not be good represented in the accuracy results. Okay. Now we have used a little bit absurd number of neurons and hidden layers, and lastly I will show you something. Because we don't have beforehand how many number of neurons and hidden layers we should use, okay? But there are some, we have some good methods and functions we can use. for example, if there is, for example, early stopping is one of them. If it begins to diverge from the original results, it will automatically cut the training of the model and give us the results. Because from this point, for example, in the in the fifth epoch, there is no need to train the model because the loss function is not closing to the zero. It is there is a divergence between the loss and validation. This is the test data, test result, and this is the results of the results of our training set here, right? Let's use instead of training every time again and again, let's come here to this point here. I will just add this weight regularizer, which means that we will decay the weights if it is absurd. For this purpose, I will import from Keras, right? From Keras dot regularizers. Import L2, not one, L2. Yes, this is a function we use for weight decay, and we insert this function inside this fit function. Whatever position you like, you can insert it. For example, after maybe, but we have to insert this one into every single, because we will not import that one into our fitting data. Here we have to use weighting decays for our inside our hidden layers, right? So let's copy that one here, not here. Maybe we can copy here. Yes, for every dense layer, we will add here a kernel regularizer parameter. We will use regularizer is equal L2, and most commonly it is used 0,001. Okay, let's train that one. We have to, this is weighting decay for the assignment that the professor asked for. Let's add this one for every single hidden unit, okay? And see the results. Yes, here. Yes, that's enough. Let's run this code. Let's run this code. Now we have added a weighting decay. Let's run that one again. And let's train our model again. Now we are training the model according to the weight decay. By using weight decay, the first performance of is even high, right? Normally it begins 86%, very high results, even in the first in the first epoch. Let's evaluate the model again. Let's evaluate. Yes, slightly better results. Let's see the visualization. What is the problem? No numeric data. And two history. Let's wait. Yes, we should write here ANN2, not 1. History, why it gives me fail? Don't write that a plot. Maybe I should begin from the beginning, because I didn't begin from the beginning. Compile here. Yes. Do you see the, Nikolai, when I train again and again, do you see the accuracy has been increased, even though I didn't change anything, the accuracy has been 100%, which means
Yes.
If you train again and again with the same data, your performance with the training data set will increase. But normally, this is a very small data. We cannot see the difference, but the performance of the Y test will decrease. Normal actual test data will decrease, which is also actually asked by the professor in assignment 2. I try to visualize this one. I try to understand what is the fail here.
I think it's because you've set, when you use the fit function, you set it to a variable. Maybe, I'm not sure, but if it would be something, I think it will be that.
Let's see. ANN2, history. Maybe we have used another history variable name here. Maybe, let's try. Without assigning any variable name. Let's train, let's see the result again. Yes, I will not focus on, I will understand the result better. But this is the way. By applying, we can also add a weight regularizer here. There is a couple of functions inside the CAS library. This is weight decay regularizer. If you use Python code for the assignment, you can use by this one by just adding that one inside here, inside every single hidden layer. Okay. I have talked about early stopping before. Let's see an example for every early stopping. And after that, I will close today's tutorial. I still try to understand. Okay. Okay. Don't focus on a lot for that one. In order to train the data, in order to prevent overfitting, we can use also early stopping. This is the latest one. TensorFlow. So if we don't know whether we should train our data 100 times or 1000 times, we can easily use TensorFlow, a good function, .keras.callbacks from callback sublibrary, import early stopping. Yes. Then TensorFlow. We will add this early stopping function inside this fitting function. Yes, let's add it. We will simply write here a callbacks parameter inside this one, callbacks. Inside callbacks, we will close parentheses, and inside close parentheses, we will use early stopping. Early stopping, yes. There is two important parameters inside this early stopping function. One of them is monitor, how it will monitor. It will monitor according to validation accuracy, because it is the most important thing for me. And there is also a patience parameter, which means that how many epochs do you want to wait after it will begin to diverge from validation accuracy, okay? If the accuracy of the training set will diverge from the accuracy of validation data set, how many epochs do you want to wait? I will wait 2 epochs are enough. You can assign 5 times, or early stopping is not defined. Maybe, yes, I didn't write correctly. Yes, as you can see, in the epoch 3, it has stopped because it has already got 100 accuracy, because we are training in the same model, in the same data, and there is a overfitting. And validation accuracy is already at peaks in the training of the epoch 3. So the model will not need to train more, 100 times, 200 times. It's a good also function we can use in order to get rid of overfitting of the training. Yes, I think we have, we can make out of experiment, number of experiments. By using these calls, we